Uh, okay, so in the second part of this lecture, just 1 second. So we have already discussed uniform flow, sink and source flow in spherical coordinates and cylindrical coordinates, and the functional forms are of course different here. Uh, the velocity potential is q equal to 4 pi r. Here it looks different. We've discussed dipole flow, but before we actually see some use of this calculation of these velocity potentials of these ideal flows, or simplified flows, we need to discuss one more, something called the vortex flow. So for the vortex flow, what you have is essentially that you have streamlines which are going in circles, and rho, which is in basically the radial direction in cylindrical coordinates. And when we refer to the density of the fluid, I shall use rho f, rho for fluid. Rho here is radius in the cylindrical coordinates, just reminding you. So v rho is essentially the velocity in the radial direction is 0. Uh, we are looking at vortex flows where z is coming out of the plane of the screen. Um, so it's a planar flow, and v theta is some gamma, which is basically the circulation, upon 2 pi rho. So suppose we consider this special kind of flow. So basically, as you go out uh, away from the center of the vortex, the v theta is decreasing as 1 by rho. Uh, then you can check that if you do v dot dl, that is some constant value over any loop, for any value of rho. If you draw a circle, then basically you get this value, the integral value dl, rho d theta, where rho is kept fixed. Rho cancels, and when you integrate over 2 pi, you get this gamma, which is the circulation essentially. So you can calculate the phi, the velocity potential, as per the standard formulas, grad in cylindrical coordinates, and that is essentially gamma by 2 pi into theta. You take the suitable derivative with respect to theta, and you'll get your v theta. So here you have integrated. The circulation is gamma, so then you can figure out its units. But for this kind of vortex flow, if you take any loop, any complete loop, which is not encompassing the center, the central singularity, you'll get circulation equal to 0. Why? But suppose you take a center along this direction, right? It will have, when you take the integral, it will have some particular value of rho 1. Now, in the radial direction, there is no velocity component. So this, and suppose you had something like this, that will give 0. And again, when you take a back integral in the opposite direction, uh, you will you'll again get minus theta, some value of theta, because rho 1, because again, so this was done at rho equal to rho 2, and this was done at rho equal to rho 1. They would cancel, and so the angular displacement would be same. And so circulation will be 0. You can take any other loop and try it out, the circulation will be 0. So this is the essentially velocity potential. So here I have summarized the velocity potentials for various cases, including vortex flow in cylindrical coordinates. And now combining, so till now we have been visualizing the flow field and calculating the various velocity potentials, and in some cases the stream function. Now what we are going to do, as we said, that it's easier to work with the velocity potentials. We're going to look at some real cases. Suppose a flow past a cylinder and a flow past a sphere, and we are going to use additions of different or sum of different velocity potentials of these ideal cases and match boundary conditions. And since we are really working with divergence v equal to 0, which corresponds to Laplacian of phi, the velocity potential equal to 0, and we know from the solutions of Laplace's equation that any linear combination of solutions is also a solution, right? This is a linear. So if we superimpose phi 1 and phi 2, which are two different solutions of two different flows. So different phi's for two different flows is a scalar field, and if we suppose superimpose such that the flow field which is created from the resultant scalar field, you take its derivative and you get your flow field of the combination, and that if it matches boundary conditions, then we know that for the Laplace's equation we have a unique solution. So that is going to be the solution of that flow field. So that's the principle. That's the principle, and that's the reason we had worked out these four cases. Now we're going to take uh, suitable linear combinations of these various scalar fields in cylindrical coordinates and in spherical coordinates. So the first thing we look at is, suppose that you have a cylinder which is lying into the plane of the screen, and you have a flow field which is going over and around the cylinder. Okay, so basically here the z points along the plane perpendicular to the screen at very large distances. The velocity is u0x. This is in Cartesian coordinates, but of course you can take the radial, you can convert it into radial cylindrical coordinates and spherical coordinates, right? So x equal to essentially cos theta. Now to figure out the value of the flow field and match boundary conditions, we say that the resultant scalar field, velocity potential scalar field, is a sum of the uniform flow and the dipole flow. Yes, so that's ansatz. Of course, people have tried it out. There's a classroom course. So here I'm telling you that just take this, and you will see that we'll be able to match boundary conditions and as a consequence describe this flow field. Right. So now the phi in cylindrical coordinates for uniform flow field is u0 rho cos theta, right? As we worked it out previously. Mm. Yeah, so this is Z. So this was calculated. So this was essentially we plotted along the Z direction. But if you take when you take it in the appropriate direction, so this was calculated along Z. But suppose you take so basically X. If you take this is X and this is rho direction, and if so basically the flow field x is rho cos theta. This is rho and this is cos theta, and that's at infinite direction, right? So this could be theta. You can just calculate the theta, and the phi of the dipole is p dot r into 2 pi rho. Okay. Now the question is, does this flow field satisfy the boundary conditions? And what are the boundary conditions? The boundary conditions will be that at rho equal to infinity, very far away from the cylinder, the velocity field is flowing along the x direction. Near the cylinder, it has to pass around it, so the velocity field will be deformed, and the velocity field will be deformed such that we'll see. And at rho equal to r, at the cylindrical radius equal to r, the radius of the cylinder, there's no component, there's no normal component. So if there's no normal component, that means that v rho equal to 0. So there's no radial component of the flow, because if there was a radial component to the flow, that would result in fluid entering the so that would result in the fluid entering the cylinder. So hence the rate V rho is equal to 0. So the phi is U0 rho cos theta, right? And minus P cos theta 2 pi by rho. Now we can calculate the velocity field of this resultant scalar potential, and that is del phi del rho. And you can call, if you calculate that, del rho, so this rho will drop off, and you will get rho square from here, because you're taking a derivative of 1 by rho with a minus sign, and hence this minus will become plus, and this is p cos theta among rho square. And similarly, you can take the derivative with respect to theta, so this will become sine theta, and this will become sine theta with a minus sign, of course, and hence, and you have a 1 by rho sitting here, so 1 by rho, it's not this minus this, but this entire thing is minus sign. So it's basically u0 rho sine theta with a minus sign, right? And yeah, so this sine theta again, so this cos theta again gives a minus sign, but we have taken the minus sign out, so hence we get this expression, right? And this row cancels with this row, hence you have u0 sine theta. So that's the message, and the question is whether it will match the flow field or not, and we'll show that yes, it does. So at rho equal to infinity, so that's very far away from the cylinder, basically what you will have is this rho will become infinity, so this term will go to 0. Moreover, rho will go to infinity, so all you have is this term for v rho, and you have this term for v theta. Does that match? Well, it will. So basically what you have is u0 in the x direction, and when you take cos theta, Vr equal to cos theta, so this is theta. If you take so this is the radial direction. If you take the component of u0 in this direction, cos theta, that will give you the velocity in the radial direction. Remember, z is into the plane of the screen. Moreover, this was this general expression for v theta, and at rho equal to infinity, this term equal to 0. So what you have is v theta equal to minus u0 sine theta. Is that correct? Now let's take rho equal to very large, suppose here, right? Then the theta direction is essentially this, because you're calculating this. This is theta, that's by convention, and the flow is such that it's in this direction. So if you take sine theta, the sine theta, you'll get the component of this is in this direction. And if you have finite theta here, suppose here you had, then there would be contribution of rho, and you see theta would be in this direction, but you know that the velocity here is in this direction, right? Moreover, if you had taken theta to be somewhere here, suppose this is your axis and you're measuring theta like this, then again theta here will be the theta vector, the theta hat would be in this direction, but the velocity is opposite to the theta direction, and hence you get this minus sign. And of course, if you're doing at a finite distance, this term would also play a role. And you see at very far, basically you can take the cos theta, which is this direction, and the theta component, and this will be the minus theta, and it matches the boundary conditions, right? So but we don't know the value of P. So we know the value of U0, U0 matches, but we don't know the value of P. And for that, to calculate that, we use the other boundary condition, which is that at rho, the cylindrical coordinate rho equal to capital R, the radius of the sphere, VR equal to 0. If VR equal to 0, then these two terms essentially will cancel, right? And what you get is P equal to minus U0. So basically this equal to 0, and thereby U0 equal to this, cause equal to this, and you can calculate P in expression in values of U0. Remember, U0 is given as a boundary condition. The speed, the velocity, flow velocity of the fluid at R equal to infinity. So if you know the P, you just substitute it here, and P was unknown previously. From here, we figured out the value of U0 by matching boundary conditions, right? Uh, and if you know the value of P, uh, then essentially you get to note you get the entire velocity field, and instead of P, you will have now minus 2 U0 R square pi. Right, and this is the simplistic form. And similarly, you're going to put in the expression of P here, the value that you have got here, and correspondingly you will put here, and note the minus sign, and we have already discussed the role of the minus sign. So so whichever is the direction of theta, the velocity is flowing opposite to that of the theta, and so we are absolutely able to match the boundary condition. Right, now what we are going to look at is a slightly more complicated case, and this will actually bring up the football example uh, which we have discussed in class. And when we had shown the football example, basically what was happening is somebody had kicked the ball, and the ball was going in this direction, the goalpost was in this direction, the ball actually curved, and the ball was rotating like this. We had shown it in slow motion. So what we are considering here for the analysis is that you have a sphere in a flow field, and the sphere is rotating. Oh, it's rotating in this direction, say. It's rotating in this direction. So here the sphere is static, and the flow is very similar to the previous case. Previously we had a static cylinder. Now we have a rotating cylinder. Of course, you can work it out also for a rotating sphere, as the case for football is. Okay, so the point is, on this surface the flow is parallel to the direction of rotation. On the other hand, on this surface, the rotation velocity is opposite to that of the fluid velocity. So that's one thing. And though here we are analyzing basically a static spinning sphere moving in a velocity field, what you could do also when you're looking at the football is move at a constant velocity with the velocity of the football, and then you would see that the air is flowing across the ball. So here what you see, that the ball is moving in the air in a so-called static air, whereas if you move into the frame of reference where you're moving along with the ball, the fluid is flowing past you, right? So we're just changing basically, what is it called, Newton inertial uh, transfer uh, transformation of frames, velocity frames. To analyze this situation, we have to look or do a trial solution of the total velocity potential of that of a uniform flow, a dipole, which we have already, uniform flow plus dipole, we have already considered. But to consider this rotation of this ball, we also add a phi, a scalar potential of a vortex, which will account for, or will be able to match boundary conditions if we take the scalar potential of these three simple flows and try to match boundary conditions. And if we can, then because we're solving the Laplace's equation, we know it has a unique solution, and that solution that we find will be the solution for the velocity field. We are solving for the potential velocity field. So we have added the velocity potential, and if we can match boundary conditions, then we are done, right? So that's what I have written here. That's what, if you find a solution which matches the boundary conditions, you got the solution to Laplacian phi. This is the sum of these three potentials to equal to 0. So here in this case, we are going to just write down u0 rho cos theta minus p 2 pi rho, right? and um, and this is the scalar velocity potential for a vortex flow, uh, right? If you take the derivative with respect to r, then we get v, this should be actually rho because we are working in cylindrical coordinates, so v rho. But if you like, in cylindrical coordinates, as long as you remember that we are working in a plane and z is the perpendicular direction, you can also work with r. I mean, yeah, so here is del phi del r, here I've changed it to rho. So we are essentially working in cylindrical coordinates, and this is the expression for the gradient of the scalar potential, that in cylindrical coordinates, right? I mean, just saying that things are self-similar, infinite cylinder, so there's no z dependence. That's why, so that's what we are using here. And basically this will drop off and we'll get exactly the same value as previously. Uh, and where we have 0 at the sphere surface and at infinity is going to match. So the matching of boundary conditions at infinity is going to be exactly the same, but things are going to be different near this cylindrical surface because we have a rotating cylinder, right? Infinite cylinder in the z direction, but we have rotation, and we have to account for the fluid velocity is flowing the same direction of rotation on one surface, and opposite to that, the fluid velocity is opposite to the velocity of the surface of the cylinder in the opposite direction, right? So here it is moving in the same direction, here it is moving in the opposite direction. uh so so we have to calculate where is v theta equal to 0, because they are opposing. At some point v theta could be equal to 0. V0 is trivial as there's no flow perpendicular to the surface, so hence when we match boundary conditions, we are going to get this u, the value of u, to be exactly u0, whatever is the velocity of the fluid at rho equal to infinity. But for v theta equal for v theta, we first try to find the so-called stagnation point, the point at which v theta, the velocity of the fluid at a particular value of theta, is equal to 0. And so what we do is this equal to 0, and u0 plus 1 plus r squared, and this rho, we are matching it at the surface, is, so that's why we write this rho equal to r square equal to gamma by 2 pi r. Okay, and if you simplify this, this will become equal to 1, so you will get 2u0 sine theta equal to gamma by 2r, and sine theta in this case will be gamma by 2 pi u0 r. Okay, now if you look, so this will be theta, or if you like, this will be theta, and you will have 2 points, you will have essentially 2 points where this value will be the same, right? So this is so here the we are taking the loop in this direction, which is opposite to that of the theta direction. Hence you will when you solve for this, this will have a minus sign, and the theta will also have minus sign, right? So because it depends upon the direction of the loop. So this will have minus sign. So you will get a gamma will be negative. Hence this theta which you also will be getting is, I mean, if you calculate in this direction, it's this minus theta, if you like, and this is again minus. So you'll have two. So you will have 2 points where the velocity of the fluid is zero, because the velocity is fluid is trying to go in this direction, where the circle, where the cylinder is trying to rotate in this direction, and same case here. So you have 2 points where you get the stagnation point equal to zero, where that condition will be satisfied with sine theta. This will be satisfied. uh, Alternatively, you could have done the same calculation where the sphere is going in the anti-clockwise direction, and then you would have got two stagnation points at this value and this value, two different values of theta. And sine theta is double valued, so it basically goes up, and before it reaches theta equal to pi, it again comes down. So there are two values of sine theta where this condition will be satisfied. So it's basically sine theta is going up and down. So two values of sine theta, it will satisfy this condition. But now suppose gamma was increasing, and gamma increased so much that its value was greater than 2 pi u0 r. So as gamma increases, for the same value of u0, sine theta is going to approach 1, and sine theta is going to approach 1, or yeah, so that corresponds to actually these 2 points moving closer together. Sine, so it's moving towards 90-degree, right? And but now, I mean, this is the mathematics, but now, I mean, you can spin the football, or in this case the cylinder, at speeds so that it is even higher than sine this value. So then what happens? So then what happens to this, right? Because sine theta can't go greater than 1. So then how do you solve it? So when sine theta is exactly equal to 1, gamma is exactly, then you have one stagnation point that's exactly at 90-degree. When gamma increases further at fixed u0, you will have a new stagnation point where both v rho and v theta will be equal to 0. But now this v rho equal to 0 is not at the surface of the sphere, right? Previously it was right at the surface of the sphere. So you will have a stagnation point, you will have a solution which you have to solve by solving two conditions, but for rho greater than r. Previously we were using the boundary condition where rho is equal to r, but now we are going, so that's where what we used here. We put rho equal to r, but now you won't have a solution for rho equal to r. Instead, what you're going to have, you have to consider rho greater than r, and the stagnation point will essentially move from the surface to outside. We'll see how the plot looks. So what you will have to now match are the two boundary conditions at, so vr, the velocity of r, at some value rho. So at the stagnation point, there's no velocity of the fluid. The fluid velocity is 0. So Vr has to be equal to 0 and V theta has to be equal to 0. Now rho is greater than R, and moreover we know that this U0, so this U from rho equal to infinity, you know that you're going to get this as U0. That is also finite. That is non-zero. Neither is this non-zero. So these two terms are non-zero, but Vr has to be 0. The only way it can be 0 is by having cos theta equal to 0, and cos theta equal to 0 for only theta equal to 90-degree, which means you know that the stagnation point will be just below here. It will still maintain 90-degree. And then at this point, V theta also has to be equal to 0. So what you do is, you know that the theta has to be 90-degree, right? So what you do is basically you multiply this entire, so V theta has to be equal to 0. You multiply this entire equation by rho square, so that this rho, so basically you'll get a quadratic equation. So basically here you will have rho square, this will be a constant term with r square, and sine theta equal to sine theta, sine 90 is equal to 1, and from here you will have another term. And then you use the Siddharacharya formula, the equation for the solving the quadratic, and if you put it, you will get rho, at which you get the stagnation point, is this formula. It's just using, you're solving just a quadratic equation. You put in the terms and rearrange, this is the term that you will get. So your stagnation point initially were two values, then as you keep on increasing circulation, it will come here, and then for gamma, even higher values, the stagnation point will move away from the surface of the sphere to here. Right? So that's the, and on this side, of course, velocity. So here you are doing ideal Euler flow. So where you are neglecting viscous terms, or even if there were viscosity, you assume a very small boundary layer, and outside that Euler flow is valid. So very close to the surface, you will have essentially a finite velocity of the fluid. Or if you have perfect Euler flow, you will have a finite velocity of the fluid. There's no friction, there is no viscosity, there is, yeah, so you essentially have, that is the solution, and you can check that matches actually, right, or even on the other surface. So 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 basically the flow profiles will look like this. Here it is opposing, so it's a relatively flat flow, whereas here there is a higher velocity. Yeah, so the current has to remain zero because we are considering incompressible fluid. So the flow has to be higher here and lower here, and and the the streamlines will essentially solve for v theta for different values of rho, for different values of rho, right? It will basically give you those equations. One is cos theta, one is minus sine theta, and you have this extra term. Uh, And whatever I told in terms of stagnation point, this is basically for low circulation, you will have two stagnation points, and the flow field will look like this. This will be more parallel, less of curvature, whereas the top one will have more curvature. Note, I'm not using the word vorticity, but I'm using just that this will be a higher velocity. And this is the stagnation point. This figure is from Physical Hydrodynamics, the four authors. So basically it says that for gamma, less than this, so that the ratio, so that sine theta is less than 1, you have two stagnation points. And for gamma greater than this quantity, you will have a stagnation point which is off the surface of the sphere. That's the basic message. The stagnation point is here. You have relatively flat lines. Of course, I don't know why the flow is like this. Okay, yeah. The last thing which I have to consider is we have calculated the flow field, but we haven't exactly explained why in the football, when you kick with a spin, the ball curves. And for that, we can just use Bernoulli's equation, which was developed, I think, two lectures before. And now the pressure is a function of theta. And the reason it's a function of theta is that velocity itself is a function of theta. And if you have streamlines, and steady flow, you have to assume steady flow. So the cylinder is rotating at a constant circulation. The flow is constant at infinity. You have a fixed velocity field in the x direction, which is u0, which is fixed. And if you have a streamline and if you have a steady flow, then the pressure near the surface will be a function of theta, because v theta is a function, because the velocity of the fluid itself is a function of theta. So there's a theta dependent, and here rho f, of course, is the fluid density. And if you substitute v theta, and you have calculated that, you just substitute that, then you can get p theta for rho equal to capital R, which is the surface of the cylinder, right? And then you can calculate the integral. So P theta is pressure, force per unit area. Now if you integrate the pressure normal to the surface and take its various components, so you basically calculate P sine theta R d theta, so that you calculate it normal. So suppose this is the flow, this is theta, and if it calculates sine theta, it will be this, or this rather, right? So so yeah, so at different values, if you calculate just the component in the direction perpendicular to the flow at infinity, and you put it, you'll see that there's a finite force, because here the pressure is less, here the pressure yeah so pressure, well, here the pressure has to be less, pressure is more, so there'll be a net force, and the direction should be, well, it should, yeah, no, if the pressure is more, why should it be in this direction? Well, I have to figure, just think a bit, maybe, so uh, so at theta, wherever there is more flow, the pressure has to be less, because kinetic energy density, right? So when you integrate it, one has to just do it the right ways, and basically you will see that there is a net force in the direction uh, which is opposing the flow, and that is the so-called Magnus flow. So just think it out a bit. So that, and basically, hence this spinning sphere football will feel a force in the direction where the spin is, or the velocity of the surface is opposite to that direction of flow. And that is essentially what the Magnus flow is all about. Okay, the last thing we shall do is basically calculate a sphere in uniform flow, no spin. Basically, again, you write down the phi in terms of a uniform flow, and here it is r cos theta, and in terms of a dipole flow, and match boundary conditions. Again, you will get at the surface Vr equal to 0, and at infinity Vr equal to x. So basically, again, del phi del r equal to 0 at very large distances. This term will drop off, r at infinity will drop off, u cos theta, it will match you. So you'll get what, so you will get this u, the same value as the velocity at infinite distances. And again, v theta perpendicular to the surface. Now it's a spherical coordinate, right? It's not an infinite cylinder. So you're calculating the flow for around a spherical surface. And if v theta has to be equal to 0 because there's no flow into the cylinder, then you can get P in terms of u0 sine theta, and all other components. So this has to be equal to 0, so P will be u0 4 pi r cube, and so on and so forth. So yeah, P will be minus u0 2 pi r cube, this is capital R, and that will satisfy the boundary condition. I'll just leave it to you to carry it out, just work it out. So that's end of Euler flow, and I shall start with Navier-Stokes in the next recording. So hopefully this got recorded. Stop recording.